Hi, Kristine. Can you hear us?
Okay, perfect. I can see you. I can hear you I mean, it makes sense why you want to kind of disable that for participants in the room, but it's a little bit hard when the speaker cannot unmute. But nice to see you all. This hopefully it's bright and shiny wherever you are. It's a very cloudy and overcast day here in Boston.
Thank you, Kristine, for stay today with us. I give a little introduction for the day, and the Dr. Sandra give introduce yourself. Good morning, everyone. It's a pleasure to welcome you to the fourth day of Orkiski Fall Fest 2025 for Qubit Hub. Today, we are especially excited as we will be joined by Kristine Rezai, who is a technical pre-sales engineer for North America at IQM Computers, one of the world's leading computing hardware companies. Thank you for joining us, Kristine, and welcome.
Sweet. Thank you so much for the introduction. I'll apologize in advance if there's any computer issues on my end, as it was quite the fight this morning to get everything working. Let me go ahead and share my
Now,
screen. Oh, go ahead.
now the Dr. Sandra, we introduce all your video and all your another things. Yes, it's okay.
Hi, Kristine. I just introduce you and give the abstract of your talk.
Oh, perfect. I'll stop then. Go ahead.
So, thank you very much for giving the talk today. So, Kristine will talk about the era of the quantum supercomputer. So, IQM Quantum Computers is pioneering the integration of quantum computing with high-performance computing. And she will begin by providing a brief overview of IQM quantum computers, highlighting recent key technical advances before presenting collaborative research done with their partners. Some of the first practical construction of quantum supercomputers have only occurred this past year. In this talk, she will describe how, together with their partner, they have built a quantum supercomputer, and she will discuss the unique scientific capability it has unlocked. And Kristine Rezai is a technical pre-sales engineer for North America of IQM Quantum Computers. In her role, she helps people learn about quantum computing at IQM by working individually with clients to assist in integrating quantum computing into their solutions, giving product demos and other presentations like this one, and supporting existing users. She has a bachelor degree in engineering physics from UC Berkeley and a PhD in physics from Harvard. Her educational background focuses on experimental quantum science, studying quantum sensing and simulation topics with nitrogen vacancy center impurities in diamond for her graduate work. After graduate school, Kristine worked in venture capital, helping build early-stage companies with the goal of solving important problems at the intersection of engineering and research before joining IQM Quantum Computers. So welcome. And now it's your turn.
Okay, perfect. As I guess that's my cue to kick started again. Thank you all for joining. Let me share my screen and hope nothing too tragic happens, as my computer's been kind of on and off last day. And in case that does happen, then I will take a short pause and kind of figure that out. So thank you for the introduction. I'll be talking about the era of the quantum supercomputer. So kind of the way that I've structured this is I'll do maybe a 15 or so minute introduction to IQM, kind of who we are, what we do, just in case you're not familiar with that. Then I'll jump into a lot of kind of recent developments that we've had where we've basically been able to integrate quantum computers with high performance supercomputers. And I'll talk about some of the lessons that we've learned from that, as well as kind of where we're going with that. So to begin, I initially had some slides on motivating why would you even kind of care about quantum computing, but I decided to kind of skip that and still kind of have more or less a general overview side of kind of the quantum computing field. And I want to start off by kind of giving you a higher level overview. In the field of quantum computing, there's a lot of different modalities. There's a lot of different quantum systems that people are interested in as using as the basis for building your quantum computer. Some of those different modalities or systems include superconducting circuits, ion traps, photonic quantum systems, quantum annealers, as well as neutral atoms. And this list is by no way in large an exhaustive list of all the platforms out there. There's a couple more that come to mind, but I wanted to kind of start you here to start you thinking about, okay, there's a lot of different platforms, a lot of advantages and disadvantages of all these different platforms. We focus on the superconducting qubit platform. So the basis for that is basically using charge, current, and energy of superconducting qubits to form the basis of the qubits themselves. You can manipulate this with electrical energy. And we also really like this because it's kind of your closest to your computing chip. So a lot of the infrastructure that's already been developed for your classical computing chips can then kind of be applied in this direction. And we're not alone in using superconducting qubits. Maybe I'll swap to the next slide. There are a lot of major players that are also interested in exploring the use of superconducting qubits as the basis for those quantum computers. So that includes us, that includes IBM, Rigetti, Google, Oxford Quantum Circuits, Fujitsu, Alice and Bob, just to name a few. Again, this is not an exhaustive list. But we do believe that superconducting qubits is one of, if not the most promising quantum solution, is at least when you're trying to build a quantum computer, there's a couple of key attributes of your qubits themselves that you really want to try to maximize. In this case, you really want to try to maximize speed, so that in this case refers to the speed of your single and two qubit gates. You also want to have relatively highly connected systems, so you want your qubits to be connected to kind of a lot of other qubits. You also really care about the qubit quality, your single and two qubit gate fidelity. You additionally want your system to have a complete or universal set of quantum gates. And lastly, you generally want to choose a system that you can actually foresee it to being somewhat scalable. And we do believe that superconducting qubits are kind of this global optimum of actually being able to kind of touch on a lot of these points. And while they may not be kind of the best in any one category, we do believe that they're like a really nice kind of global optimum. And if you compare some of like our statistics and our performance with the performance of other quantum computing or of other quantum computing groups that are focused on superconducting qubits, our performance and our scale is really at least on par with some of our competition. So we've achieved single and two qubit gate fidelity in some of our test devices of up to and over 3 nines. Our QPU scale, we currently have 54 qubits, soon to be 150 qubits. Our gate speed very fast, generally less than 20 nanoseconds. Readout speed also comparably fast, around 170 nanoseconds. And I think the connectivity of our systems is kind of an interesting point where we're connected to at least 6 nearest neighbors in some of our devices. And I'll get to this in a little bit because I think it's kind of it's a cool little tidbit about that really separates kind of our systems from other systems in the same class. Who we are, what do we do at IQM? We really focus on building the full stack superconducting qubit quantum computers. So that goes all the way, we start at step 1, where we do the design and the fabrication of our own quantum processing units. We lay out the circuit, we have our own fab that does this. We really focus on having ultra fast gates and fast readout with high quality to qubit gates. But it's not enough for us to just make the chips themselves. We have to also think about how do we integrate those chips with the entire system such that we can get the best performance out of the chips themselves. So we do the full stack integration. We do all the electronics that kind of go to and come out of the chips themselves. We put all this in a Blue Fours dilution refrigerator and kind of package everything up completely. And then on top of that, we have a dedicated software team that writes the software stack really tailored to make it easy to use, say, in conjunction with high performance computing clusters, as well as make it easy to use on the cloud. And we also want to make it, again, as user friendly for the user. So whatever quantum SDK you're using, we want to make sure that that is translatable to using our system. So we support using CUDA-Q, Qiskit, Cirq, Crisp. We're available on Amazon Bracket, as well as Ticket, which is Quantinuum's software as well. We also support. So we try to support kind of as much software as possible to make it as easy as possible for the user to access our hardware. And lastly, kind of on top of that, we have this amazing algorithms and error correction teams, which they then think about, okay, can we, build some tools that make it easier, for example, for the user to kind of run their algorithms on our hardware. And sometimes some of the results, say, of our error correction team that come out of this can then kind of be fed all the way back into the initial step, where then some of the learnings here can then go ahead and they can form some of the ideas and the basis for what the next generation of QPUs should look like. A little bit about who we are in numbers, and again, maybe this is just I'm trying to give you a sense of kind of who we are, what we do. So we're about 314 employees. I'm based in the US. There's three of us in basically North America. The rest of the employees are mostly in Finland as well as in Germany. Since quantum computing is a highly technical field, we're about, or a little bit more than a third PhDs. We're also very well funded. We just raised our Series B of 320 million US dollars. So we're currently well funded and looking to use that money to grow and expand and really advance along our roadmap. I think what makes us interesting as well is just the number of systems that we've built and the number of full systems that we've sold. So we've built at least 30 full systems, as well as we've sold at least 15 full systems to our customers. Again, founded about, say, 7 years ago at this point, a very multinational company. So it's really a pleasure to work here and just get to work with some of the best people from all around the globe. And I'll say that, yeah, we have 150 qubits chip in development, and currently the cloud users, it's more than 2,000 at least at this point. So we really focus on both on-prem full stack hardware that kind of looks like what's behind me, as well as also cloud-based access. We have kind of a unique combination of critical infrastructure. So we do things from, like I was mentioning, kind of having our own dedicated fabrication facility that's based just outside of Helsinki, Finland. Kind of the reason why we want to have our own fab facility is that really lets us kind of really optimize the quality of the chips that are really coming out of the fab, especially if we don't let external users in, and we can basically control which machines they use which substance. And that also really helps our iterations cycle to have everything in-house. So we have everything from that to this assembly line. So we have this hallway of kind of row after row after row of full quantum computers. It's really interesting to see. So we have this assembly line that basically helps us kind of lower the production costs. We can build now up to 20 full systems per year. It's really, truly remarkable. And then kind of lastly, we have this quantum data center that's mostly located in Munich, Germany, that hosts our quantum cloud, this IQM resonance. And we do have some further investment plans to expand some of these capabilities. Just to kind of flash what we offer. So again, our on-prem offerings go all the way from like a 5-qubit Spark device that actually kind of looks like this, really tailored for research and education, mostly to education, all the way up to kind of the flagship systems of up to 150 qubits. And then on the cloud, we offer kind of a lot of different systems with different topologies as well. So we offer both a 20 and 54 qubits kind of crystal lattice system, as well as a star system as well, that I'll kind of show up. I'll show you what that looks like in a second. But really, kind of the cloud access really kind of gives you that lowest barrier to entry, kind of where we're spread out along the globe. And this will actually come into play when I talk about our efforts to actually integrate quantum computers with high performance supercomputers and what we've learned from that. But we've delivered at least 10 full systems at the first time. Kind of our first delivery in North America is to Oak Ridge National Lab in Knoxville, Tennessee, but we've delivered kind of throughout Europe as well as throughout Asia. And we've actually sold more on-prem full stack quantum computing systems than any of our competitors have in the last 5 years. So we have a lot of experience in actually kind of building the full system and then kind of installing it and integrating it. And I think it's a very interesting question of what does it actually take to basically install these types of systems in data centers or wherever you need to install it, because there are certain things that you have to keep in mind when you're installing like a quantum computer instead of when you're installing like a rack in like your data center. I'll just kind of put in a short plug that we're actually offering some free credits for students. So feel free to sign out. You can use Qiskit again to access any of our our devices. So if you sign up at resonance.meetiqm.com, you can basically get 30 free credits per month. Again, we're making kind of a push for people to get on our cloud. And the last thing I'll say that's more or less promotional is we're also offering this IQM Academy, which if you want to learn more about quantum computing as well as see some Jupyter notebooks that are using our system, feel free to go to academy.meetiqm.com and you can see all these free educational resources. But I'll kind of take a step back from there and kind of go into a little bit of the science. Yeah, I want to kind of focus on some of the science that we've done on our systems that may or may not be of interest before kind of hitting the main topic of this talk. So we've always been really focused on these high performance building blocks of how do we make our qubits themselves and our systems kind of as performant as possible. And kind of one of the major steps that we took, I guess it's now been more than 3 years ago at this point, is actually this tunable coupler architecture. So in between, say, two qubits on our chip, we have something called a tunable coupler instead of like a fixed frequency coupler. And what that essentially allows us to do is we can actually have, in this case, faster gates, higher fidelity. And this actually kind of really helped start to decrease some of our 2-qubit gate errors that you see. So this was kind of introduced in 2022. You could see that kind of over the time, some of our performance in our test devices have kind of continued to decrease, or some of the performances continue to increase, the errors decrease. So you've had some, say, calibration improvements, some increased coupling, improved coherence. So currently in our test devices, we've reached 2-qubit gate fidelities of 99.93. Of course, these are in our test devices and not in the devices that are currently available. But I think it's worth doing this type of research to try to understand how to minimize errors and how to really kind of get these best performant building blocks such that then you can take this and then translate that to your larger devices. In addition to that, we've been playing around a lot with quantum error correction. I won't go into the details too much in this case, but we've been playing around with other codes aside from the surface code because our systems have higher connectivity. So we've been playing around, for example, with tile codes, as well as looking at, and I'll show you this on the next slide, looking at some of our higher connected systems and trying to explore what type of quantum error correction schemes these types of systems would enable. So I will maybe leave you with this, and I'll leave you with the archive links in case you want to kind of take a look and learn a little bit more. But now I'll kind of talk a little bit more about our technology and kind of what makes it useful and kind of how are we scaling up from that? And again, I'm kind of maybe a little bit, I don't want to say disorganized in this beginning, but I kind of want to give you a flavor for everything that we're doing before I kind of get to the topic at hand. So one unique thing about IQM is that we actually offer two unique QPU topologies. So how our qubits are actually arrayed and connected to one another is a little bit different from other superconducting qubit groups. So maybe I'll start on the left with this IQM crystal. So you can see the qubits themselves in this blue and these tunable couplers, which basically mediate this 2-qubit interaction, is in kind of this bluish screen. And what this device is useful for is it's useful because it has relatively high nearest neighbor connectivity. So if you look at like a qubit kind of in the middle, it's actually connected to 4 nearest neighbors, as well as you can do fast parallel gates. This is really kind of the workhorse for a lot of the algorithms and applications that our teams kind of go forth because you have like this relatively high connectivity, but you can also do things in parallel. So for example, you could do simultaneously like a 2-qubit gate between, say, these 2 qubits and these 2 qubits. And there's, a high degree of parallelization in this system that makes it really nice. However, we also now have this the star system where, again, your qubits are in blue and your tunable couplers are in this bluish screen. And what you'll see here is that all of your qubits are connected to every other qubit through the use of this computational resonator, which you could think of it basically as like a harmonic oscillator with very minimal anharmonicity in this computational resonator. And what's interesting about this system is that you have this effective all-to-all connectivity where each of your qubits are effectively connected to every other qubit through this central resonator. And that's kind of interesting, especially if you want to look at some quantum error correction schemes where you want, say, a higher degree of connectivity in your system. So that's kind of, one interesting avenue. The other interesting avenue is that you can do things like beyond two-level computation. And what I mean in this case is that your central resonator, again, has some harmonic, or has some, basically it's a harmonic oscillator, has some kind of, ladders of energy levels, and you can basically excite this to higher level states. You can do a lot of interesting like qubit resonator physics, and there's a lot of interesting like science that's come out of this system. I don't have any links, but if you're curious, I'm happy to send you some links of the science that's come out of this. And then we also have pulse level control for all devices that we have. What we just announced as well, and this is new, hot off the press as of I think like 2 or 3 months ago, we introduced how we're going to scale both systems. So the crystal system, it's maybe not so surprising that you can think about basically just replicating the pattern. You kind of have a unit cell and kind of replicate that. But we actually just announced this constellation system, which this is new. So this is how we're planning on actually scaling the star systems. And what you see here is a bunch of qubits, say, connected to one another, again, through these kind of resonator blocks, where every qubit now is actually connected through a resonator to 12 other qubits. So for example, this qubit is connected through this resonator to five other qubits. It's connected to this resonator to, I guess, in this case, 4 other qubits, and it's connected to this resonator to like 3 additional qubits. So every qubit is connected directly to 12 other qubits. And then there are 2 times as many qubits as there are resonators. So actually, every single qubit and every single resonator can be involved in a 2-qubit gate simultaneously. So this has an incredibly high level of parallelization. At least whenever you're running your gates, you can do a lot in parallel, as well as it has this advantage of having a very high degree of connectivity. So this is where we're going. We don't have any devices available as of now in this, but we just announced this topic, and we're definitely open to any feedback or questions or thoughts about kind of where we're going with this. And just to kind of give you a sense, again, this is just a map of the connectivity. So again, this is then a pictorial description of, okay, this is what the system looks like, and then this is just kind of showing all the connectivity. So if you're looking at like this qubit, you can just see just how many other qubits it's currently connected to. So it's a very, very interesting system, and we're starting to kind of release more and more information about what we're planning on doing with such a system. So that's at least hopefully like an interesting intro to IQM, what we offer, some of the technology that goes into our hardware. I will now swap over to this topic of HPC QC integration, which will basically be kind of the majority of this next, whatever, 35 minutes or so that we have. So maybe I'll start off with high performance computing, and what is the point even of high performance computing. So we went to the websites of a lot of different HPC centers, and we kind of were trying to poll different mission statements to try to understand, what purpose do these HPC centers serve. And it seemed like we were able to kind of distill this into 3 different categories. So one is to help enable research and innovation. So one of the points of these HPC centers is to try to give scientists, engineers, companies access to the needed compute resources for whatever it is that they want to study. A second thing that we kind of distilled was that another major point is to help advance technology. So how do you test and deploy new architectures, accelerators, and programming models? And lastly, there is kind of a national or strategic role, maybe strengthen competitiveness, security, scientific leadership within the country and in some area. So at least that's kind of what we distilled from this. Why am I not able to advance? Here we go. But also kind of going along with some of those pillars, sustainability is now more and more thought of as kind of a core goal for some of these HPC centers. And kind of here are some snippets of kind of news segments from a lot of different places. And it is true that basically as the compute demands grow, also the need for kind of the power that you need to sustain some of these data centers, as well as kind of the water capabilities, they are not necessarily the most resource efficient. So there is also now this push to more sustainability when it comes to, say, building the next generation of data centers. Currently, the landscape of HPCs. So again, kind of some of these studies, again, one of these emerging trends is sustainability. And I'll point out some numbers too. So some studies predict that, again, this demand for electricity will increase by anywhere from 160% to 200% just in these next 5 years. So there people are now thinking about, okay, how do we actually make these more efficient? And there's also some studies that show that the global computing is now likely responsible for between 2.1 and 3.9% of greenhouse gas emissions. As well, so you can see that, yeah, 1 megawatt data center consumes quite a lot of water every year as well, in addition to the amount of power that it consumes. So it really, I mean, I think part of this motivation is that it is kind of worth looking at alternative forms of compute that may end up helping with this energy challenge. Um, Another reason why you may want to also look at quantum computing is that we were actually NERSC, which I believe is associated with the Lawrence Berkeley Lab. They just released a paper on the archive that looked at quantum computing technology roadmaps, and kind of were also looking at use cases from their own workload. So this was actually, they were able to look at the workload on their supercomputer, the Perlmutter, and they were able to basically kind of categorize each of these workloads into kind of categories of what they what they were. And then they went ahead and they highlighted which of these types of problems could potentially be applicable to a quantum computer or a quantum computer plus a high performance supercomputer. And it turns out that over 50% of the workloads that are running on their supercomputer are also applicable to like HPC plus QC workflows. And that's also really nice to know that, yes, a lot of what's already being run on these supercomputers some of which like can be offloaded and could be helped by quantum computers. Let me advance. Here we go. So I like this slide a lot. It's a nice question of, okay, why would you even bother combining? I mean, I'm trying to get motivated. Why would you bother combining quantum computing as well as supercomputing? If you look at like quantum computing itself, quantum computers, they're not good at all types of problems. They're really strong at certain types of problems, including those problems with like very high complexity, but low data problems. So if you think of like your traveling salesperson, your optimization problem, your quantum chemistry problem, and that's because they combine these unique superpowers of superposition and entanglement to basically enable like a new type of compute, new type of algorithm. But if you look at like your more traditional supercomputing, supercomputing also has its strengths. It can be really strong at like parallelized problems, big data problems, really general purpose computing. And our goal here is that if we can combine like supercomputing with quantum computing, can we say unlock some new capabilities in optimization, chemistry, material simulation, quantum machine learning? And we're not the only people that are looking into combining these two. There was also a really nice paper that more or less recently came out, also on the archive. This is from collaborators from groups at Oak Ridge National Lab, Rincon, and CSC. And I really like this quote. I won't read it kind of to you word for word, but basically what they did was they acknowledged that even fully error-corrected quantum computers are not going to be suitable for all computational tasks, even if they can be universal computing machines. Basically, what they discovered was that these quantum computers will likely serve as like quantum accelerators for high performance computing. And also, another thing to note is that while these quantum computers can accelerate this purely classical computing, traditional HPC is also really crucial for getting the most out of quantum acceleration. So there's this synergy loop between quantum computing and supercomputing where you really need your quantum computer to help accelerate some points of your workload, but you also really need your supercomputer or some classical computing resources to also get the most performance out of your quantum computer as well. So really, there is a motivation for trying to understand how to best combine these two resources. So you might ask, okay, like what are I kind of started this off by talking a little bit about the quantum supercomputer. Like what even is a quantum supercomputer? It turns out that there's kind of three key elements, at least, for this quantum supercomputer. I mean, in one case, yes, you need a quantum computer to make a quantum supercomputer. You also need one of your classical supercomputer, as well as you need to think about how you develop this middleware for executing these scientific workflows. So these are really kind of the three things that keep in mind. I mean, currently the quantum computers exist, the supercomputers exist. There is an interesting question here that I'll address of actually how do you make this middleware, both kind of the hardware as well as the software for executing some of these scientific workflows. Here we go. And then we try to kind of think about, okay, what practically, like, what do you actually need to make a quantum supercomputer? And like, can we actually address and can we actually achieve these things? So on one hand, you need, I mean, of course, the physical integration of HPC plus QC resources. And I don't want to say it's a shame, but to this date, a lot of the majority of HPC plus QC workflows were really studied using QPU simulators and not actual QPUs. And we do believe that some of these simulators, they can't fully reproduce kind of the noise of a real system. Thus, some of these simulator results don't actually kind of accurately reproduce what it's like to have an actual kind of quantum computer on-prem. Kind of another thing that you really need is you need to basically orchestrate this using some existing infrastructure. So how do you manage your quantum resources along with kind of all other resources that need to be managed by your HPC center? You need to be able to do things like schedule jobs, like offload and cancel jobs, like kind of have a lot of those same capabilities that you have in more traditional HPC. The last thing that you need to do is you basically need to start thinking about what are the actual building blocks for these HPC plus QC workflows. And we're now only beginning to explore some of these brand new capabilities. And we're also trying to think about how do we create like standardized building blocks that would help speed up the adoption of HPC plus QC workflows. So I'm going to address each of these, and I'll tell you about what we've done in each of these categories, as well as kind of where we're going in each of these categories. So I'll start off with like the physical integration of HPC plus QC resources. And this is something that I believe are very much kind of leading. So we took the first steps of integrating a quantum computer with a supercomputer back in 2022. So back in 2022, in Finland, VTT had one of our 5 qubit quantum computers, and they were actually able to connect that with the Lumi supercomputer. So that was kind of one of the first steps that was taken, and that was really the first time that a hybrid service connecting a supercomputer with a general purpose quantum computer was actually open to researchers. So that was done about 3 years ago. Very small quantum computer, but at least we're showing that we can connect them and that we can do these kind of hybrid workflows with them. Back in 2024, that's when things really started kicking off and really picking up, at least for us. So in 2024, we commissioned a more powerful system where we now installed our 20-qubit quantum computer at the Leibniz Supercomputing Center. So we connected it to the SuperMUC NG supercomputer. And this all was commissioned, and this all began back in June 2024. And since June 2024, some high-impact research has now begun basically on this system using these integrated HPC QC resources. And they've also developed a software framework, the Munich Quantum Software Stack, that they use for workflow orchestration. Taking that, so we had this experience now almost a year and a half ago. We've taken this experience and we worked with the partners at LRZ to actually write one of the first guidebooks detailing some of our learnings of integrating this HPCs with a quantum computer. So this is a paper that just came out on arXiv. You can see the link here. So this paper basically details kind of all the lessons, not all the lessons, but some of the lessons that were learned when practically integrating a quantum computer with a high-performance supercomputer. And I'm going to highlight maybe two of the key takeaways from this computer. One of the key takeaways, so it shouldn't really come as a surprise that integrating a quantum computer, in particular in this case a superconducting qubit quantum computer, you have stricter facility requirements than HPC. And what I mean by that is that there are kind of requirements on how much like vibration your systems can handle, what the humidity is, what the temperature is, what the electromagnetic fields are in the vicinity of your quantum computer. So what we found is that, yes, on one hand, these superconducting qubit quantum computers have stricter facility requirements than kind of more traditional kind of racks in data centers. But we were actually able to kind of navigate some of these stricter requirements by using a careful site selection. So generally, whenever we install these devices, we survey the site and we come up with a couple potential sites. So we were actually able to kind of navigate this and find a suitable place. So while there are stricter requirements for installing quantum computers, it can still be done just with a more careful site selection. And kind of the second main kind of output that came from this is that our quantum computer could actually be operated for more than 150 days without any human touch. So no, we didn't have to have, say, anyone on staff kind of fiddling with the quantum computer, except for a weekly 5-minute liquid nitrogen refill for the dilution refrigerator. So it was nice to see just hands off some of these systems can be when we've integrated them into the data center. And that's really nice, as I think a lot of places don't necessarily want to have a staff scientist kind of on site to help kind of fix and maintain some of these devices. So this at least details some of our first learnings. There will likely be more that comes out from this. How do I advance? Okay, cool. So that's a little bit about what we've done and kind of doing the physical integration of HPC plus QC resources. Likely more will come out along that line. Now I'll switch over to talking a little bit about how do you orchestrate the system via existing infrastructure. So let's think about, okay, how do users even kind of typically interact with a quantum computer? So generally users interact with a quantum computer that kind of sits in some data center, like, and you get access through it through the cloud. So usually, kind of you're typing on your computer, and you'll submit your job, and that will go basically to the cloud. That job might sit in some queue before it's executed on your quantum computer. Your quantum computer will basically run, and then some results will then be relayed kind of back to the cloud, and then those will basically then come back to you. So this is kind of the typical workflow for how a lot of users currently are interacting with quantum computers. But there's a kind of a subtler challenge here when you're actually thinking about how to integrate these resources in HPC, because in HPC, there's a more delicate balance of resources. You cannot block resource usage in your high performance computer. You can't, say, have anything sit idle for more than, say, a certain period of time. You really can't have your supercomputer sitting idle. It needs to be running at almost maximum efficiency. You also need a fair usage of some of these rare quantum resources, so you also can't have your quantum computer sitting idly. And you also, you have to think about how do you accurately bill and make permissions, and all of this generally needs to be done within some existing framework that's likely already sitting kind of at your supercomputer. There's likely already a software stack that does this, and kind of the question is, okay, how do you then make the software such that this can also interact well with your quantum computer, your quantum resources? From this experience, collaborators at the Munich Quantum Valley, at the Technical University of Munich, and as well as at LRZ, they just released a paper as well on this HPC QC framework. So their HPC QC framework is called the Munich Quantum Software Stack. They wrote up a really nice paper about it. I won't go through and summarize it myself, but basically what they're trying to do, and this software stack is currently in production use, they're really trying to standardize this quantum computing access for scheduling, job management, and device queries. And they also want to try to introduce this HPC integrated scheduler and compile infrastructure that minimizes this idle time and optimizes hybrid workflows. So feel free to download and read the article, but this is kind of, the direction that we're going, is that we're working on with our partners on some of these different things, and there's progress that's happening along all fronts. Lastly, I'll talk a little bit about what it means to provide these building blocks for HPC QC workflows and what these workflows kind of even look like. So if you think about HPC plus QC algorithms, and if you think about the types of workflows that are done, in this case, they generally fall into two broad categories. There's some classes of algorithms that are iterative, so you'll have this rapid iteration between tightly integrated QC and classical resources. So your quantum computer will execute some part of the workflow, and then you'll need your classical computer, and they'll kind of go back and forth. Like variational quantum algorithms are one such example of an iterative workflow where you kind of go back and forth between quantum and classical resources. There are also another class of hybrid quantum classical algorithms that are more sequential in nature. So in this case, you'll have maybe an HPC intensive classical pre-processing, and then you'll submit your job to the quantum computer, and then you'll have some intensive, say, classical post-processing. And I'll show an example of what this looks like momentarily, but yeah, kind of as I said on the previous slide, this is one example of an iterative workflow. So this is a variational quantum algorithm. It's, again, yeah, a key example of an iterative workflow. The idea is that, yes, you have some initial state preparation, maybe using classical computation, and then your quantum computer basically goes and it executes some quantum circuits. You'll get the measurement results out. You'll kind of create a cost function. There'll likely be a classical optimizer. And then from this classical optimizer, you'll kind of figure out some better values of your circuit parameters that kind of goes all the way back in. And you kind of end up with this loop between your quantum circuit execution, your classical optimizer, and things kind of go back and forth between this quantum ansatz and your classical optimizer. So this is just kind of an example of one hybrid workflow that's iterative in nature. Another example that's sequential is this quantum assisted Monte Carlo, again, example of a sequential algorithm. The kind of the points here, there's a lot of steps in this, but the point here is that there's really intensive kind of classical pre-processing that happens before you come up, say, with your trial wave function that then you basically send to your quantum computer, and then there's some really intensive classical post-processing that happens. And we've started to kind of poke around in this type of problem space, so you can actually see a link here to one paper that came out of our group earlier this past year. I will say that there's also, say, a clear supercomputing contribution to kind of in general HPC plus QC resources. You can think of like, why would you need a classical computer at the very beginning? You might want to do things like quantum state preparation, noise-aware compilation. Maybe you're using some application libraries and then basically sending this to your quantum computer. And then the results, there are things you can also do classically kind of at the end of your computation, including like post-processing, maybe you're doing quantum error mitigation, maybe you're doing quantum error correction, and all of these three things, they may need intensive classical computing resources. So you can kind of see what the contribution is of supercomputing to quantum computing. How do I move forward? There we go. I will also say that from some of these kind of from these results, we've done kind of a lot of interesting science so far on our system. Here are three examples. Each of these examples is an example of using a hybrid workflow, though I'll say that only the middle example was done at LRZ on this hybrid integrated HPC QC system. Kind of the first and the third examples, they're both basically using the cloud with some additional classical compute resources that they had access to. But each of these three examples here, you can see the link to them. So we've done some experiments, or actually not us, collaborators and colleagues have done projects in industrial chemistry where they saw, say, a 200x increase in speed modeling of a complex molecule using a 42-qubit QPU that we have available. I'll actually talk about this one in more detail in a second. So this is a solution chemistry experiment where we're actually able to do very sophisticated modeling of proton transfer using intensive HPC and quantum resources. And lastly, you can also do some interesting, in this case, material science, but it's basically simulating phase transitions in materials, again, also using this hybrid quantum plus classical computer. I do want to go through, since I have some amount of time, I'll go through one of these use cases. So actually, I'll go through the middle use case, but the methodology is very similar in this case. The type of hybrid algorithm that they ran is very similar for each of these three cases. So maybe I'll go through it as I think it's interesting and it kind of highlights exactly how you can interplay these quantum and classical compute resources. So the type of hybrid algorithm that was used in this study that I'll go through an example right now. So the type of hybrid algorithm that we use is called this quantum selective configuration algorithm, and it's a very, in my opinion, promising quantum chemistry simulation technique. It departs from VQE, and the idea is that you're basically using your quantum resources to make the final solution on your high-performance supercomputer a little bit easier to solve. So what you're doing here in this case, and I'll go through the workflow first, and then I'll show you the example, and then I'll show this integrated kind of with that example. So initially what you do on your quantum computer is you'll figure out some input state. How you generate your input states is a little bit complicated, but then from that input state on your quantum computer, you basically use that quantum computer as a sample to sample from this state, and then you'll basically end up with a bunch of bit strings that then correspond to these select configurations. So what you'll end up doing then is, instead of having kind of the full basis state, you can then diagonalize your Hamiltonian kind of in the basis of some of these, kind of in a much smaller total basis set, and you'll do your diagonalization. And then from this process, you'll end up, say, calculating the ground state energy, state vector in the subspace. There's different things that you may want to kind of get out of this process. But the idea here is that you're basically using your quantum computer then as basically a sampler to basically make kind of the final computation a little bit easier in this case. So the problem, and so this is something like our group didn't do this, but the Coveney group worked on this project at the University College London, and maybe I'll go through it, as I think it's a very interesting example, and I think I have 12 more minutes left. So what they were able to do is they were able to model this proton hopping between water molecules. So what they studied was they studied this hydronium molecule, which is the protonated form of water. But kind of in practice, this exists in these two solvated forms, these eigen and these Zundel cation. And the idea here is that you have an extra proton, and this extra proton can basically hop between these adjacent water molecules in the solution. And this is known as this Grotas mechanism, which has, I guess, some importance for a lot of biological processes. So what they did, at least in the study, was actually consider this planar form of the Zundel cation, where this free proton can basically hop in between these two adjacent water molecules. So that's at least what they did. What they showed, so all this can be done classically. So what you see in the solid line is the full configuration interaction. So this is like the complete classical solution, kind of best classical solution that you can get. What you see in the dashed line is Hartree-Fock. So that's an example of like a classical approximation method. And what you'll see here is that what's going on is basically this like oxygen separation is basically being changed, and you can see basically the energy landscape for where this single proton should exist. So you can see that basically as things are extended, so right now things are extended, there's kind of two potential wells where this proton can exist. It's going to go back to that. So you could see, again, there's a large separation. Basically, your single proton might want to sit at the wells, but then when you move these two molecules together, then you'll have kind of this one potential minimum kind of in the middle. So essentially, yeah, they're looking at basically different oxygen separations. And basically, this ideal proton transfer mechanism basically occurs when this potential energy surface is flat, which occurs about now at about 2.6 angstroms of separation. But to kind of give you a sense, so this was done classically. Doing full configuration interaction is resource intensive. What the point is they wanted to understand if they could use this QSCI algorithm to basically be able to reproduce the same accuracy that's given kind of here, but also then use, say, less classical resources to reproduce that result. So in overall, they basically kind of combines these unique benefits of classical and quantum computing. So they're able to use classical computing for kind of looking at what's going on in the solvent. And then at least for the quantum computer, I realize I have 10 minutes left, so I will kind of it'll take me 2 more minutes to go through this. But in any case, they use the quantum computer basically to look at like this active region where they basically mapped every qubit to one valence electron that's going on here with these two oxygens plus this hydrogen. They're able to use some symmetry arguments to basically reduce the number of qubits that they needed to just 16 qubits. They basically mapped out the rest of the system to density functional theory. And then again, using this QSCI algorithm, basically mapping the system onto the quantum computer, use the quantum computer to sample, basically projected this Hamiltonian into this configuration subspace, and then basically solve the reduced system classically. And what they're able to get. So this is what's below here is basically the chemical accuracy. So this is what you get with the full configuration interaction. This is what Hartree-Fock gives you, which again is a classical approximation technique. This is what DMRG gives you, which is also another classical somewhat approximation technique. And this is the results of kind of the hybrid quantum classical. So they were actually able to achieve this chemical accuracy, at least for some points along this proton transfer coordinate. And what they're able to see is that it also outperforms DMRG at many steps along the way. And each of these curves basically corresponds to a different spacing. Conclusions and future outlook. So I'll say that I think that we can successfully claim that we built a quantum supercomputer. Our quantum computers can be co-located with HPC. These software frameworks needed to integrate these quantum accelerators exist, and we're starting to see some of the building blocks that we need to grow these HPC QC resources. So we do see kind of have a very positive outlook on this. We see a bright future where these quantum accelerators really open a lot of new possibilities in scientific computing. One last thing I'll say, we've also released our development roadmap, so go check it out if you're curious. And thank you so much. I am open to any and all questions. I hope that was interesting.
Thank you for an excellent talk. And yeah, so we have some questions and
Okay.
just, some clapping, the virtual clapping. So
Should I turn it off the share mode, or should I just leave it in the share mode? What would you prefer?
maybe turn off the share mode that we see more of the people. Yeah.
That makes sense. Then I can actually see what's
What's
perfect.
going on. Yes. So we have one question. So we need to use quantum APIs and manage access to quantum APIs. So do you have an opinion about the API question?
Oh gosh, I do not. This is the software stuff. I am, to be honest, is my possibly one of my weaknesses. I think yeah, I guess what exactly do you mean by that? Is at least kind of I'm trying to go back to that slide.
So
Perfect.
Adriana, you want to speak up about what you wanted to ask here? Which it refers to? So with the application, we can follow up on that. Okay.
Yeah.
So let me see that I unmute you.
How to manage access to quantum APIs. I mean, let's see.
Adriana, you
Actually, let's answer the previous question in the chat first, and then I'll come back since we have 6 minutes.
Okay, so yeah.
Let me see. How do you envision the role of open source software or community-driven development evolving around hybrid quantum HPC platforms? Oh, that's also an interesting question. Yeah, I think that there should be actually a large kind of a large role for a lot of open source software and community-driven development. It's an interesting question now of how do you also standardize this? So I can also see standardization being more or less something that like we shouldn't, I mean, it's I work for a quantum computing company, so I would say, it'd be nice to have some influence on what the standards are, but really I think you do need more or less an open community who's not kind of, attached to any one system or any one platform to at least come up with what these standards should look like, and kind of at different, say, layers in the software stack, like what should be open and exposed to, say, your developer, and what should not. So there's definitely kind of a role for the software community, I think, in this.
Great. At the moment, Adriana, I said you, yeah, you said you can, but I'm not sure how to un.
Oh, perfect.
Hi. Hi, good morning. I think there's morning, right? So
Yeah, it's
thank you very
10
much.
a.m. almost.
Oh, okay. So good morning. Yeah, because I'm looking in the most with DevOps.
Hmm.
So this is why I'm asking about the API,
Hmm.
because I don't understand very well this
Hmm.
part. If it's with, yeah, I mean how it works with the API, because yeah, I know it's more like a DevOps role, right? Like need to do authentication, authorization, networking.
Yeah, it's actually
Mhm.
it's pretty simple. Maybe I'll answer maybe a slightly different question of like how do you actually like practically run and submit jobs, or is that and like kind of what authentication you need kind of on both
Yes,
ends.
exactly. Yes.
Yeah. Yeah, so generally like there's I generally do all my programming like using a Jupyter notebook, but there are certain commands that I need to do to basically, say that I'm connecting to this quantum computer, and then I have like a token basically that I can that's assigned just to myself that I basically use at some point kind of there will be a query where I need to basically put in my own identifier that then says it is me, so therefore you should bill me, and you should also see kind of what groups I'm involved with. So aside from basically like putting in the URL of the quantum computer and putting in kind of my own token, there isn't so much more like authentication that you need to do, because kind of once I basically put both of those in, both identified myself and said I want to use this quantum computer, then kind of
Mhm.
things are pretty straightforward.
Oh, okay,
Okay,
great.
Yeah. I
thank
can
you.
give
Yes.
you examples of, yeah, if you look at the IQM
Mhm.
Academy, there's tutorial notebooks that actually show what this workflow looks like. So there's
Oh,
places
great.
there where they have like a block of text where they basically call the quantum computer, and then where they put in their own identifier. So if you take a look at, I can put this in the chat.
Oh, thank you. That's very nice
Yeah.
from you.
Um, yeah, if you Google this, then you'll see. Oh, there's interesting questions here. Okay.
Yeah, so we have the next question. So how do you
Yeah,
see the
thank you.
panorama of quantum computing in Latin America?
Oh, it's an interesting question. I hope you guys would inform me, since even though I mean I'm based in the US, but we're trying to understand kind of what the ecosystem also looks like in Latin America. So um I don't know. I don't know if I have a good impression, but I'm open to kind of hearing about it. I mean, having events like this, I think are really great to raise awareness amongst students and amongst the community of what's going on in the field. Is there's definitely this upward trajectory, and I think it's important to kind of get in on this while you can, and kind of, try to, build up awareness around the technology.
Yeah, that is absolutely what we exactly want to do with events like this. So
Yeah.
it's started with a workshop in February. So the question probably aimed at like whether you have heard about more. So that is, we are happy to hear about this. I think we're taking a last question because the next speaker is here. From your point of view, are the most important challenges in fabricating the superconducting quantum chip? What are the
Oh gosh. I've never fabricated these chips before, but I think from what I've heard, and this may not be the most important aspect, but really focusing on the quality, the impurities in the materials. I think one of the main um, detriments of superconducting qubits is the number of two-level systems that might exist in the material, that will then affect the coherence properties of your qubits. But I think there's a lot, I mean, of course, being able to replicate kind of the fab process, not having holes in your devices, as well, is quite difficult. There's a whole host of challenges, as well as maybe actually I'll add one more. The timeline it takes us to make some of our devices, especially the larger devices, that is also a huge challenge, and being able to iterate quickly through this process.
Thank you so much. Thank you for
Great.
the great answer. Thank you for having the time on Sunday.
Of course, I guess I will hop off the call and thank you all for tuning in. Have a good one.
You too. Thank you so much.